In this example, we're going to determine the shortest path from vertex S to vertex T. And that's actually why I put those two vertices, I've enclosed those vertices in circles, just so that we can see the start and end a little bit clearer. The numbers in red are the weights of all the edges, okay? So what we're going to do is we're going to come up with a path, or try to determine a path from S to T where the weight of the path is as low as possible. Hence why it's called shortest path, okay? The numbers could represent distance, for example, distance in kilometers, could represent a dollar amount, so the amount of money it takes to travel from one vertex to another. It could be a time, so number of hours, for example. So we want to try and come up with a path that's going to take sort of the least amount of whatever it is that we're trying to determine, the lowest number. Now we can also see that there's so many ways of getting from S to T. Okay, we can go S, A, B, T, for example. That'll be 1 plus 12 plus 6, which is 19. We can go S, E, F, T, which has a weight of 24. There's S, C, D, B, T. I mean, there's so many paths, and to list them all can be quite arduous. You could be there for a while, in fact. Just listing all the various paths from S to T. So we're going to take this a little bit more methodically and really attack this just with a bit more method to the madness, so to speak. So what we're going to do, we're going to consider the vertices that are 1 unit away from S first. Okay. So these are the vertices A, C, and E. And we're going to slowly sort of migrate over to T eventually. So to get from S to A, okay, the quickest way to get from S to A, and you have to consider sort of the roundabout ways to get to these vertices as well. From S to A, the quickest way is going to take 1 unit. Okay. From S to E, okay, we can either go SCE, but SE is certainly the more direct way, but it's actually the way that's going to give us the lowest weight or the least cost. That's 8. Now SC is 4. But you can see that it's also, to get to C, we can go via A. So SAC is in fact going to take 3 units, 1 plus 2. It's going to be quicker than it is to go direct from S. So I'm going to put the number 3 there. Now, this is where it can get a little bit confusing, and this is why, to help to alleviate some of that confusion, I'm going to use now a different color, different color pen, to look at the vertices and to determine the weights of the paths to the vertices that are now 2 edges away, or the next set of vertices away from S. So now we're getting closer to T. So let's have a look at, for example, vertex F. We're going to consider the numbers in blue that are going to help us to calculate the weight of the path to F. So to get to F, we have to choose one of these 3 vertices. So from E to F, 8 plus 9, that's 17. We can go from C to F. Okay, so that's 3 plus 6, which is 9. So in fact, they're the only 2 ways to get to F. So that path there and this path there. Okay, 3 plus 6, 9. That's certainly the least of the 2 options. Now, to get to vertex D, we can either go AD. Okay, so 1 plus 7, which is 8, or we can go CD. Okay, also that's 3 plus 5, which is also 8. So we can put an 8 there. So they happen to be equal in length. That's okay. That can happen. Now, B, the only way to get to B is in fact via A. Okay. So 1 plus 12, okay, is 13. But you might say, well, hang on a moment. We could get to B via D. In fact, since we've just computed D, could we use D? Even though originally we're using the numbers in blue, could we then now use the numbers in green? Yes, you can, actually. In fact, 8 plus 3 is 11. So we can actually put 11 there rather than 1 plus 12, which is 13. Yes, it's a little bit more of a roundabout way, but it still gives us a lower number, okay, even though we're going about it a little bit less, a bit more indirect, I guess. Now, finally, we've determined that these 3 vertices. Now to get to T. To get to T, we can either go via B or via F. Okay, so 9 plus 7 is 16. We've got 11 plus 6 is 17. So 16 is it. Okay. Hope that makes sense at this point. We still haven't determined what the shortest path is yet. We know what its weight is. We know it's going to be 16, whatever, 16 kilometers, $16, 16 hours, whatever. But let's now determine how to actually trace out the path, which is the shortest path. Now, starting from 16, okay, we need to now start backtracking. Okay, 16, and what you do now, you start subtracting the numbers in red. 16 minus 6, and it should equal the number that's next to the vertex. So 16 minus 6 is 10, but we have 11 here. So it's actually not, can't use this path, it must be this path here, because 16 minus 7 is 9. Okay, so what I'm going to do is I'm going to draw in the shortest path here in blue. Okay, now from F, 9 minus 4 is 5, but we have an 8 here, so it can't be this one here. 9 minus 9 is 0, but we have an 8 here, so it can't be this one here. 9 minus 6 is 3, and it's most certainly this edge here. Okay, now from C, 3 minus 4 is negative 1. We actually want a 0 here because obviously you're at the start, so it's not costing anything. 3 minus 4 is negative 1, but we want a 0. So it can't be this edge here. Okay. 3 minus 2 is 1. Okay, so it looks like it's this edge here. And then finally, from A back to the start, 1 minus 1 is 0, and that works. In fact, what other choice do we have, really? But it's just a way to verify that we actually did the right thing. So therefore, the shortest path, okay, so this is what we did there, was backtracking. So the shortest path is S, A, C, F, and T. Okay, and the weight and the of weight 16.